So this chapter is called as addressing modes. It's a very simple concept with a fancy name. We have already learned a little bit about addressing modes, but we'll go into full depth in this chapter. For example, we have seen instructions like this, right, in the first chapter. What does this instruction do? This instruction basically copies whatever data is there in memory location 2080 into register R1. That's what it does, literally, right? So here if you notice, how are you addressing this register? See, in this place, so if you think of this as your whole instruction, this is your opcode, right? You can think of this as giving the address of the register itself. You could have multiple registers, as we have seen in the first chapter, right? Here you could just give the address of the register itself, right? So because you're addressing the register, this is called as register addressing mode. Very commonsensical stuff, right? So here the third part, so you have your opcode, you have one operand or one register here, and here you have the memory location. So what happens as soon as this instruction is executed? The control unit goes to this memory location on your main memory. If this is your main memory, right? So we have already learned this in the previous chapter. I'm just recapping it. In the main memory, it goes to location 2080. Right, the control unit goes to 2080. Whatever data is stored here is now taken and placed in my register R1. That's how exactly everything will work. So here, what are you addressing? This is called as direct addressing mode. It's called direct addressing mode because I am directly giving the address in the main memory. Okay. So oftentimes, instead of writing this as just 2080, the typical notation that is used in many microprocessor textbooks or computer organization textbooks and on Wikipedia articles is to place this in square braces. So the moment you place this in your square brackets, this implies that what you're referring to is the direct address. So this is just a notation, right? Instead of just writing 2080, we place this in this square braces to imply that I'm directly addressing this address here. That's what it means, right? So very simple. We have seen register addressing mode and direct addressing mode already in the previous chapter. But there are many more types of addressing modes that we learn in this chapter, and they're mainly required if you think about it. So for example, take pointers, right? In pointers, what do you have? You have the address. How does again, this is all, if you have seen C programming language, we have pointers, we have arrays and things like that, right? So if you want your microprocessor to compile programs which have pointers like C programming language, and if we want our microprocessor to have instructions which can handle pointers very gracefully and very easily, then we could have different addressing modes. These addressing modes are called as indirect addressing modes, right? We learn about them. We learn about them in lots of detail. Similarly, in arrays, what do you have? You have contiguous locations, right? In some memory address, you may have your first value. So this is basically like an indexed thing, right? Because this is your array index. This is your array index, and in contiguous memory locations, same type of data is stored, right? So if your programming language like C, C++, or Java has arrays, how do you now translate this effectively into machine level instructions, right? So address modes is all about how do you address data effectively. That's what it's all about, right? There are multiple types of addressing modes that we learn with tons of examples and solve problems in this chapter, but this is the high level overview. So let me also give you all the types of addressing modes that we will learn of. Broadly, again, I'll keep using this term AM to refer to addressing modes. Addressing modes broadly are of two types: sequential control flow addressing modes and transfer control flow addressing modes, right? So transfer control flow. What does transfer of control flow means? So in the previous chapter, we learned about jump if 0, right? We learned about this instruction, right? We have learned about jump if 0. What does it do? It transfers the control flow to whichever location we want to transfer it to, right? Again, we learned about JZ when or jump if 0 when we learned about the PSW flags, right? So here, using these addressing modes, we can transfer the control flow, or we can jump, or we can go to, or we can implement loops, we can implement if-else conditions, all of them using these two addressing modes. And both of them are memory-based addressing modes. They will address, they're used to actually point to some memory addresses. Okay. So similarly, there is a sequential control flow addressing mode. Because this is transfer of control flow, this is sequential. In this case, what happens? One instruction executes after another instruction sequentially. Right here, you can jump from one location in your code to any other location using commands like jump 0, jump not 0, etc. Right? Again, within this, you have, again, this is mostly used. Sequential control flow addressing modes are typically used for addressing data. This is mostly used for addressing the next instruction that you want to execute. Right? So this is mostly focused on instructions. Remember, at the end of the day, your addressing modes have to worry both about instructions and data. Right? Both of them are important because you need to fetch both. Very often, you need to fetch your instruction and your data from memory. Again, we'll understand this much more in detail as we go and look at what a relative addressing mode is, what base register addressing mode is. When we go and understand each of them, again, right now what I'm giving you here is an overview of everything that we will learn. Again, within sequential control flow, there is register-based addressing modes, which is nothing but the simple register addressing mode that we have learnt about here. You're simply addressing a register. That's all. Similarly, there are memory-based addressing modes. We'll study all 6 of them. Again, within these 6 of them, there are subtypes. Okay, within these 6 of them, there are subtypes. We'll learn all of them slowly, steadily, one by one. Okay, but this is the big picture of all the addressing modes that we'll be studying as we go forward. Okay, first we'll start with the again, register address mode is trivial, right? So we'll start with the simpler ones, and by the end we'll go to these more complex transfer of control addressing modes. Okay, so first and foremost, register addressing mode, very simple. Let's take an instruction like this. Very simple instruction, add R0 R1. So this is my opcode, right? This is my opcode. This is my first register. This is my second register. What does this do? Again, all this data is there in my instruction register, which is a register itself. We have talked about instruction register, right, in the previous chapter. All of this is stored in the instruction register itself, because while it is in the instruction register, this whole instruction is executed. Let's not forget that basic fact. Okay. So now how does this work? Okay. So what does it achieve first? Let's write that down. What does it do? It does R0 equals to R0 plus R1. This is what it achieves. Now the moment, so in your register based addressing modes, if you have opcode followed by an address, this address is the address in the register file. What is a register file? It is a set of registers in which all of my registers are it's a set of registers, and I can address any register. Suppose if I have 0 to n-1 registers, I can use log n base 2 bit address, right? This is my address to the register itself. Here there is a very important term called the effective address. So effective EA. So there is this term, very important term when we are learning addressing modes, called as effective address. The effective address basically means it is the address where the final data that you want to address resides. Right? Very simple. Effective address is the final address where the data that you want resides. Okay? Very simple definition. So in this case, your effective address is nothing but the register name or the register number, because that's the data that you want to pull and apply this addition operation. Very simple concept, right? Now there is this concept called as memory references. Again, we have seen this concept earlier also. How many times are you referencing things? That's very important, right? If you think about it. So first of all, when you are decoding, see, remember, I load the instruction. I have my program counter. I use the program counter to load the instruction from main memory to the instruction register. Right? Once I load it into the instruction register, then what happens? First, we perform instruction decoding. If you recall, in instruction decoding, what do? We look at the opcode and understand what operation needs to be performed. Now to do this, look at this. In the instruction decoding stage, we are interpreting what the opcode is, which means we are referencing. Remember, instruction register is also one of the registers in your CPU. It's also one of the microprocessor registers. So in the instruction decoding stage itself, I am performing one memory reference. Memory reference basically means I'm actually going and looking up in the memory. But here, of course, this one memory reference is not going to the main memory, This memory reference here basically refers to the register memory reference. I'm performing one register memory reference. Because remember, your instruction register is also a register. So in the decoding stage, I have to go and interpret what this opcode is and what we need to perform from now. In the execute cycle, how many memory references are there in the execute cycle here? In the execute cycle, I have to read the data which is there in R0 and R1 into my ALU. Look at this. How does this work? I need to perform, again, this memory reference is a register memory reference. There is one memory reference here. Here I need to perform one memory reference to read R0 into ALU. One memory reference here by register memory. That's what I mean. So here I have one register memory reference. Here I'll have one register memory reference, one register memory reference. I have to write this. So there is a write here, there is a read here, there is a read here, there is a read here, right? So in the execute stage, while R0 and R1 are loaded into the ALU and the output is stored in R0, how many registered memory references do I have? I have 3 registered memory references. So I have 3 registered memory references. So to execute an instruction like this, what is the total number of registered memory references do we have? We have total of 4 registered memory references. Many people get confused and say we only have three register memory references, because they say, okay, I'm reading R0, I'm reading R0, I'm reading R1, I'm writing into R0. But many people forget to account for the fact that in the instruction decoding stage, we also read the data from the instruction register, especially the opcode, which itself is a memory reference, because your instruction register is one of the registers, right? We should not forget that. Again, register based addressing mode is a very, very simple concept here, very easy to understand, and we have used this extensively till now, right? So now let's go and look at the other one. So there is this thing called implied or implicit addressing mode. Some books use the word implied, some books use the word implicit, right? This is also a very, very simple concept here. Now what does this mean? So let me introduce you to some new extra commands. Okay, there is this command called STC. This means set the carry flag. It means set the carry flag. What does this result in? This results in your carry flag being set to 1. That's what this results in. Similarly, some microprocessors have this command called CLC, which means clear carry flag. So clear your carry flag. So what happens here? Your carry flag becomes 0. Right here, look at this. Your carry flag is part of your program status word, which is itself called as a flag register. Where is your program status word stored? It's stored in a special register called the flag register. Right? Let's not forget that. So what happens here in this case? So if you take this instruction, what does it have? It has only an opcode. This is a 0 address instruction. Look at this. This is a 0 address instruction. It has only an opcode, nothing else. There is no explicit address given to me. But this is implicitly going and changing the carry flag, which is part of the flag register or the PSW. So in here, there is addressing happening. So when you execute this, in the execute cycle, look at this. So in here, in the execute stage here, we had 3 memory references, right? Here in the execute stage, there will be one memory reference wherein we go and change this flag to 1. Okay, we don't care what its current value is. This is a simple write operation. We write the value of 1 into this carry flag, into the carry flag which is stored in the PSW. So implicitly, there is one register memory reference happening. So one register memory reference is happening implicitly. Look at this. This is there in these 2 commands, or these 2 instructions are there in many modern microprocessors. They are there, right? They're just simply 0 address instructions with simply opcode. But even though there is no explicit address, they go and perform a register memory reference because they're setting or resetting one of the flags in the flag register, right? So very important. So here it's called implied because the actual register that we have to modify, or the flag that we have to modify, is implied in the opcode itself, or it is implicit in the opcode itself, right? Very important. Now imagine if I have not a general register CPU. These are there in general register CPUs, right? These are there in general register CPU organizations. Imagine if I have a stack CPU. In a stack CPU, what do you have? Imagine if I have an instruction like add. Here I'm not giving any explicit addresses. Here I'm assuming that everything is stored in the stack. Again, the stack itself is stored in the memory. Remember, the stack itself is stored in the memory, right? So while executing this add instruction in a stack CPU, implicitly we are asking it to pop two operands from the stack, perform the operation and push it back to the stack. Wherein, look at this, what is happening here in the execute cycle of add. First, okay, so in the execute cycle, first we pop, right? So we are reading it from the stack here, right? And we are storing it into the accumulator, right? We are storing this into the accumulator. Then we pop again here, store it into the temporary register. These two things go into the ALU. The ALU performs the add operation. And what does it do? It again writes it back to the stack. So look at this. Look at what's happening. There is a read operation here from the memory, right? There is a read operation. There is a read operation. There is the arithmetic operation here. There is a write operation again. Look at how many multiple memory references and operations are being performed when you're using just, see, look at this. Here I'm not giving any address here, but the address is implicit that we have to pick from top of the stack and then push it back to the top of the stack. That's why these are called implicit addressing modes. Typically, your zero address instructions are your typical implied or implicit addressing mode instructions. Very simple concept here, right? Now let's look at immediate addressing mode. Okay. So what does immediate addressing mode mean? This is something that we have not seen extensively. So I'll give more details about this. Okay. Here, what do we have? We have an opcode. Look at this. Here we have an opcode and some data in here. Typically, again, in here, what do you have? You have an opcode here. You have a register, right? You have register addressing mode here. And here what you have is called as immediate addressing mode. Immediate addressing mode. Now, what does the immediate addressing mode basically mean? Let's understand that. Look at this. This is my opcode. I'm using a register, which means I have register addressing mode here. Look at this. This instruction has two addressing modes. This part we are using register addressing mode. This part we are using immediate addressing mode. In the immediate addressing mode, as the name says immediate, the address is not actually the address. It is actually some data. So in here, what happens in here is literally your R0 gets the value of 23 in hexadecimal. So this is thought of as a constant. So whenever this is actually used as a constant, this is a hexadecimal constant. Or again, in here, your effective address, there is no effective address here because whatever you have in the address field is nothing but data or a constant. Okay, that's very, very important here. That's why this is called as immediate address, because immediately within the instruction itself, you have the data that you care about. You don't have to go to main memory or you don't have to go to any register here. Okay, so in here, data is part of the instruction. This is often used for constants. So imagine if I have a statement like this: int a equals to 56. Here, what am I doing here? I'm taking a constant integer in C programming language and assigning it to variable a. Now imagine variable a is stored in some register. Then what can I do? I can assign this variable, this constant 56 to this variable. So when you have instructions like this in high level programming languages, they can be effectively represented using just one instruction using immediate addressing mode. Because the data that I care about is immediately there in the same instruction itself. Very simple here, very, very simple. Of course, there are some disadvantages and advantages here. For example, here we are copying the data from whatever is here to this, right? So in immediate addressing mode, whatever we are using to represent the immediate address can be used as the source of the data. We cannot use it as a destination of data. For example, imagine if I have this. Imagine if I have this. What does this mean? This means implicitly into this 23 base 16 store the data that is there in R0. This is meaningless. This is meaningless. Can you say this? Can you say 56 equals to a? Int 56 equals to a in C programming language? No, 56 is a constant. How do you assign a variable value into a constant? Makes no sense. So immediate addressing mode cannot be used as a destination. Here this is the destination. Here this is the source. Right? So immediate addressing mode cannot be used as a destination to store the data. It can be used as the source. For destination, it makes no sense. Again, additionally, there is one more important concept here. Because we are using the address bits. Look at this. This is the address part of the opcode. Like for example, you may have 16 bits for this.
because you have 16 bits, there are limited number of bits to represent this constant data. Because there are limited number of bits, the range of numbers that you can store here is limited. So the range is limited. So this is also range limited, right? So if you want to store instead of 1 byte number, if you want to store 2 byte number here, but imagine if you have only 16 bits for this address or for this immediate addressing mode location, right? For this, imagine if you have only 16 bits. Okay, if you have 16 bits, sorry, imagine if you have 8 bits, then you can store this. But if you want to store a 16-bit constant into R0, because R0 itself could be a 16-bit register, you can't do that because you only have 8 bits here, but you want to store 16 bits, right? So there are always limited number of bits for this immediate data or in the immediate addressing mode. Because you're literally writing down the data, the number of bits may be limited because the instruction itself could be fixed size with a limited number of bits to store this, right? That's very, very important. Okay, cool. This is again very simple. This is mostly used for constants. This is mostly used in programming languages to store constants. Okay, let's take a very simple problem here, right? Very simple problem here. So imagine I have a microprocessor which is multiplexed address 0 to address 23, right? Multiplexed. Okay, it's a multiplexed thing. So how many address bits do you have now? How many address bits do you have? You have 24 address bits. How many data bits you have? You have 24 data bits, right? Because you have 24 data bits, you have a 24-bit microprocessor. This microprocessor, even though it's not told to us, because the address bits are 24 bits, AD0 to AD23, right? And it's all multiplexed, okay? We have 256 two-word instructions, okay? So we have 256 two-word instructions, okay, cool. And we have 128 microprocessor registers. For 128 microprocessor registers to address this, we need 7 bits, right? We need 7 bits for this. The instruction format is opcode, register, register, immediate. Okay, there are 4 parts to this. This register will take 7 bits. This register will take 7 bits, obviously. Obviously, it will take 7 bits, right? So, and it says, my instructions are two-word instructions. Look at this. My instructions are two-word instructions, which means this whole instruction length, because we know one word is 24 bits, right? Because we have a 24-bit microprocessor. 2 words basically means this whole width of the instruction is 48 bits. Very simple. And how many instructions do I have? 256 two-word instructions. It doesn't say about any other instructions. I just have 256 instructions. To represent 256 instructions, 256 is 2 power 8, which means you have 8 bits for your opcode. Very simple. 8 bits here, 7 bits here, 7 bits here. Now how many bits are left for your immediate now? This is 15. 15 plus 8 is okay, 1 second. 15 plus 8. Sorry, 14 plus 8. I'm sorry. 14 plus 8. Right, sorry. 7 plus 7 plus 8, right? So 14 plus 8 is 22. So 48 minus 22 is 26 bits. So 26 bits are left for your immediate field here. Now what is the question being asked? What is the largest unsigned number that can be stored in the immediate field? What can you store in the immediate field? Look at this. What is the largest unsigned integer? Okay, unsigned integer. So in 26 bits you can store 2 power 26 minus 1. That's the largest number you can store. Look at how we arrived at the solution by understanding step by step. First we understood that there are 24 address bits and 24 data bits. Because there are 24 data bits, this is a 24-bit microprocessor or one word. So this is the length of one word. So the moment we found that two-word instructions, I have two-word instructions, which means each instruction is 48 bits. And I have 256 such instructions, which means I need 8 bits for this. I have 128 processor registers. So this is 7 bits, 7 bits. We computed the immediate bits now. Once we compute the immediate number of the bits in the immediate field, this is simple. That's how you have to break down a problem and solve it step by step in computer organization. Okay, so now let's look at the next type of addressing, right? Very simple addressing. This is called as direct or absolute addressing mode. Very commonsensical. This is what we have seen. Look at this. We typically represent this with this square braces. So what does this mean? This means this means into R0, store whatever data you have in R0 plus whatever is there in the memory location 2080. So in the memory location 2080. So what is happening here? Here you have the register addressing mode. Here you have the direct or absolute addressing mode. So imagine if you have direct or absolute addressing mode, this address itself is the effective address. Remember, whatever address is here, this itself is the effective address. Because what you do now is you use this address, right? You use this address to reference the main memory. The main memory goes to that address. Whatever data is here is copied into the data bus and is sent back to us. Very simple concept, right? Now you might wonder, what is this used for in the real world, right? When you write code in high-level programming language, how does this whole thing gets used? Again, you learn some of these concepts in compiler design also. Okay, because what does compiler design do? In compiler design, we learn how to translate this code into machine level language, right? So one of the biggest use cases of direct or absolute addressing is basically static variables. What is a static variable? Imagine I have a code like this, int main, right? Int I equals to 0. Now here, look at this. I have to store, like in this case, what I have to do, this I may be stored in memory somewhere. Right? So into that memory location, I have to copy this constant called as 0. To represent this constant, I could use immediate addressing mode. So here I could use immediate addressing mode. If this I is not stored in a register, but if it is stored in, let's say, some memory location, I have to use direct addressing mode then. Right? So again, when this gets translated, so how does this get translated into machine level language? This could get translated into move 2080. Let's assume I is stored in memory location 2080 and I have 0. So I'll just say 00 base 16. Okay, this could get translated into, this line could get translated into this. So what am I saying? My I, again, when you learn compiler design, you know how the compiler uses a table to store the information about what is the memory location for each variable that I have. Oh, I completely forgot. In C, I think in the C syntax, the static, if I have a static variable, I need to use the keyword static, right? What are static variables in C programming language? You can check out our course contents in C programming language. But static variables are variables whose lifetime is the whole program execution lifetime itself. So this int I will be present even if I go out of this program and even if I go out of this function and execute another function. Right? So those are called static variables. Again, I did not mention this clearly in the pseudocode, but in C programming language, static is the keyword that you need to place before int itself to say that this is static variables. Again, static variables, what is the lifetime of a static variable? The lifetime of a static variable is the total program life, the total program execution time, right? So if you want to create static variables, for example, imagine I is a static variable. So let's assume I is placed in memory location 2080, right? So what do you do now? So into this memory location, you will have this value 00. And again, again, we learn this in compiler design. The compiler actually has a table called as a symbol table. Again, we learn this in compiler design. The compiler has a table called symbol table in which it says I is a static variable and I is stored in memory location 2080, right? So the translation from the high level programming language variable name I to the memory location 2080 is done using something called a symbol table in compiler design. Okay, but obviously coming back to our computer organization concepts, direct or absolute addressing mode basically means you're directly addressing whatever is there in the main memory. Very simple concept here, nothing fancy.